Man, I don't get this physics problem at all, man.
Huh. I think I got it.
Really?
We gotta go try it out though.
Let's go. Yo, Bindu, we need your help real quick.
Absolutely, I'm ready.
Alright, come on, let's go. Alright, just stand right here, don't worry about it.
Okay.
Alright, so Nate, theoretically, what you said, right? If I push him,
Huh?
you should be able to push him back. Hey, don't worry,
I agree
okay?
with that. I agree with that.
Whoa, 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 whoa!
You know what? That makes sense. I think I can do this problem now. Thanks, man. I
What
appreciate it.
happened?
Hey everyone, my name is Eilman, and my partner's name was Helen. Today we'll be going over the two boxes problem. So the problem in context, we have two boxes, one blue denoted as mass MB and one red denoted as mass MR, are sitting on a level, horizontal, frictionless table. On the left edge of the table, the blue box is in contact with a spring with a constant K that has been compressed by distance x initial. Starting from rest, the blue box begins moving to the right across a frictionless surface until it collides with the red box. The boxes, now stuck together, slide towards the right edge of the table, where they encounter a spring identical to the one on the other side of the table, meaning it has the same spring constant K. We are asked to determine the maximum distance or displacement of the second spring once the two boxes come into contact with it. Based on this description alone, we can assume that most, if not all, of these forces will be along the x-axis. So here's a system diagram for this problem. The diagram was made in the slideshow, so they're not identical, but they have the same K constant as mentioned before. So in each row in this diagram represents the problem after a small amount of time has passed. In row 1, you can see that the spring on the right is compressed to the max with the blue block. In the second row, the blue block has been completely launched from the spring and is on its way towards the red block. In row 3, the collision has occurred, and in row 4, both blocks are moving together, while in row 4, the spring has been compressed all the way, with both blocks pushing against it. And this compression is what we were trying to solve for. So here's what we already know. As mentioned before, most of these forces will be along the x-axis. We know that the blue box, after its initial release, experiences no friction, no net force, and no friction after launch and before the initial contact. So energy is conserved in the system until the collision occurs. We also know that after the collision, they stick together, but not through friction. So we treat them as one system after the collision. We know the work energy theorem states that net external work is equal to a change in energy, and because there is no work done on the blue box after launch, the energy conserved until it impacts the red box. Here's some more info on what we need to know to solve this problem. So these are the necessary equations and tools we use to solve this problem. The first is the work energy theorem. This theorem states that the work done by net forces on a system is equal to the change in kinetic energy of the system. So we have the integral of f dx is equal to the change of x. Next, we have kinetic energy, which is the total energy an object has when it is in motion. And this can be modeled by kinetic energy is equal to 1/2 mv squared, where m is mass and v is velocity. Next, we have the spring potential energy, which is a variation of potential energy that is associated with springs and elastic objects. This is modeled by 1/2 kx squared, where k is the spring constant. These equations will help us solve for the maximum compression of the spring. So here are our calculations that were hand-drawn. Helen did these with special colors just for you guys. So in the beginning, we saw in the diagram that the spring was compressed, meaning it has spring potential energy, and that was transferred to the blue box, giving it kinetic energy. So with the conservation of energy, this means that the spring potential energy should equal to the kinetic energy of the blue box. So we can have the equation V is equal to square root of K over mass of blue box x initial. Initial momentum of the system must be the same as after they collide. So we can set up the equation mass of blue box multiplied by velocity plus mass of the red box x is equal to the mass of the blue box plus the mass of the red box multiplied by velocity. Now on the bottom left, these equations can be rewritten as velocity is equal to the mass of the blue box times velocity over mass of the blue box plus mass of the red box. And then this turns into velocity is equal to mass of the blue box over mass of the blue box plus mass of the red box multiplied by the square root of k divided by mass of the blue box x initial. Here k is the spring constant. Here's part 2 of our calculations. It's a little bit messy here, so I'll try to walk you guys through it. So we have kinetic energy of both, which will be equal to the spring potential energy, as there is conservation of momentum. So we have the equation 1/2 mass of the blue block plus mass of the red block multiplied by velocity squared is equal to 1/2 of kx squared. So this we can rewrite as 1/2 mass of blue block plus mass of red block multiplied by mass of blue block divided by mass of blue block plus mass of red block, which is again multiplied by the square root of the k constant divided by mass of the blue block multiplied by x initial squared. And this is equal to 1/2 kx squared. So then we can go on to 1/2 multiplied by mass of the blue block plus mass of the red block multiplied by mass of the blue block divided by mass of the blue block plus mass of the red block squared, which is multiplied by the k constant divided by mass of the blue block without a square root this time, multiplied by x initial squared, which is equal to 1/2 kx squared. So then we can simplify this down to mass of the blue block divided by mass of the blue block plus mass of the red block, kx squared initial is equal to kx squared. This can once again simplify down to x final is equal to the square root of mass of the blue block divided by mass of the blue block plus mass of the red block multiplied by x initial. So this will give us a maximum distance the second spring will compress. As with any physics problem, we have to sense make. So we have our equation x final is equal to the square root of mass of the blue block divided by mass of the blue block plus mass of the red block, x initial. We can also have this written as m is equal to the square root of kg divided by kg plus kg multiplied by m. The kg's cancel and we're left with m's, meaning m is equal to m, making our equation true. Here we're going to analyze the solution with some more sense making. The final answer shows that the final position of the second spring is dependent on the masses of the blocks, as well as the initial position or compression of the first spring. This makes sense because the problem states that the two springs are equal in behavior, so their spring constants should be equal and dependent on each other when supporting the same system. Since the two springs are equal in behavior, if the displacement for spring 1 is increased, the displacement in spring 2 would also increase proportionally. This would also be true if the compression of the spring 1 was less. Spring 2 would have a smaller final compression. In addition, if the masses of either block increases or decreases, the second spring's final compression will be impacted accordingly. For the similar problem comparison, we compared our problem to the two astronaut problem. In the two astronaut problem, there are astronauts A and B. Before, astronaut A is going 20 kilograms per meter per second towards astronaut B. This results with three different outcomes that we have to calculate. The first one, astronaut A is at rest while astronaut B does not have a current velocity. In outcome 2, astronaut A is going backwards at 5 kilograms per meter per second, and we have to find the outcome for astronaut B. In the third outcome, the astronaut A is going towards astronaut B at 5 kilograms per meter per second, while we do not know the outcome of astronaut B. I really like this problem because there were many different aspects to it, and it was very similar to this problem as well. The situation happened in a frictionless environment, just like the one with the boxes. We have to use kinetic energy calculations as well as the work energy theorem to find the final momentum of each different situation. In this problem, momentum was conserved, whereas in the boxes problem, it was energy that was conserved. However, the setup and solutions of the two problems were very similar, with the initial and final momentum of the astronauts being equal, which is similar to the initial setup in the calculations for the boxes problem. Now this brings us to our final conclusion. Our conclusion is that the maximum compression of the second spring, after being impacted by the two boxes stuck together, is equal to the equation x final is equal to the square root of the mass of box blue divided by mass of box blue plus mass of box red multiplied by x initial, with boxes being represented as MB and MR respectively. Through sense making, this is shown to be a valid answer and representation of the situation. This was overall an interesting and fun problem to think about and solve. In the future, I'd like to solve and look at this problem with both friction and gravity included and see how that affects the second spring's compression. Will increasing the mass of the blocks linearly affect the spring's compression or not? These are things we'd both like to find out in the future, and hopefully we'll be able to this fall in Physics 212.